number one. Welcome to the ASHRAE conference, by the way. This is workshop number one, the construction, operation, and maintenance of high-performance systems of large central plants and distribution systems. Just a couple of quick things before we get started with the presentations. Please turn off or mute your cell phones out of respect to the speakers and to your fellow attendees. Photographs and audio recordings of the presentation are not allowed. The presentation will be available during the virtual conference sometime later throughout the week. Usually it takes about a day. There's a day lag for the upload of the virtual conference. The views of the authors here do not necessarily reflect the position of society, nor does their publication imply any recommendation or endorsement by society. If you have not already, please use the ASHRAE 365 app to complete the speaker and session evaluations and surveys. In the app, you'll want to go to the 2019 Winter Conference information. You log in with your ASHRAE login information and password, and find the session in the schedule. Again, this is workshop number one. So we're going to get started now with the formal portion. So my name is Sonia Ponce. I am chairing this workshop. Again, it is the construction, operation, and maintenance of high-performance systems of large central plants and distribution systems. It is in part sponsored by TC 7.3. Which meets on Tuesday afternoon from 1 to 3:30 in Grand Ballroom A in the Omni Hotel right across the walkway there. Because this is a workshop, we've got three presenters here, but I'm going to introduce all three of them at once. We've got one brief presentation for you, and then we've got some activities planned for you. So, the introduction of your speakers. Your first speaker today is going to be, your first speaker today is going to be Tim Anderson. Mr. Anderson has 28 years of engineering and managerial experience, and he's worked at Applied Engineering Services for about 18 years. He is currently serving as principal, and his engineering background includes district chilled water, hydronic and steam generation, refrigeration, and, of course, HVAC. Tim has extensive experience in managing projects and working with contractors, vendors, and plant maintenance personnel. Our second speaker today is going to be Mitchell Swann. Mitch has over 30 years of experience in areas of engineering, design, project management, and consulting for a wide array of clients in diverse industries in both the U.S. and abroad. Mitch's career has included engineering design of HVAC systems, piping and control systems, project and department management, commissioning, forensic engineering, that sounds really fun, right? And expert witness engagement. He's also done a bit of dispute resolution and project execution consulting. He's worked for clients on commercial, industrial, and high-tech projects, and he's worked in both the A&E, E&A, and design build firms, as well as construction management. Our third speaker for today is Terrence Rollins. Terrence has, for the past 30 years, been actively engaged in the energy and facility management. He's had 6 award-winning projects, including 2 Energy Star Awards at the Peter Rodino Federal Facility, the Robert A. Rowe Federal Facility, and 4 additional awards when he worked for the Department of Defense. His work includes project management, and Terrence is a graduate of, my apologies here. He's got a Richard L. Shaw Scholarship Award for the Ferris State University HVAC&R program. And he was presented the AEE's Energy Professional Development of the Year Award in Region 1 in 2013. He is also a published author with the title RHC Global Energy Solution Master's Thesis. And those are our presenters for today. I'm going to now bring up our first speaker, Tim, and they will introduce or just kind of welcome each other in succession.
hear me now? Can you hear me now? Okay. Good morning, everyone. High performance buildings and large system, that's what we're going to talk about today. Before we start, though, I got to say, I saw some high performance offense yesterday. I'd like to see a show of hands. Who watched the Chiefs and the Colts yesterday? We got a few out there. Mr. Mahomes and his high-powered offense really put it on the Colts. And hey, better luck to them. I hope they get past the Patriots. Anyway, so my perspective on this is on the construction side of things. This is our objectives for our workshop. I would like to acknowledge I took some material from the ASHRAE Chapter 12 Systems and Equipment. That comes from TC 6.2. This rough agenda of what I plan to bring up today. So, before you start, you need to decide on what you're going to do for your high performance building. And there's a lot of options out there. I just want to bring that up. If you walk into a building and you're sold on a certain system, okay, but I think you ought to look in your locality and see what you have available. There's everything out there from the air-cooled VRF systems to what I call the lake water cooling effect systems that really cut down on your energy use. So as a comparison, this just gives you an idea of what an energy modeling process will do for you for different systems to help narrow down what works best for you. So if you look at this, there's 3 different systems. This is spread over a year. Total HVAC energy for this building being modeled. And up at the top right there, there's alternate 1, baseline, alternate 3. I'm sorry, I got to explain this. For some reason, we put the baseline in the middle, and then alternate 1's on the left. HR coils is on the right. So you can see alternate 3 in the summertime is a pretty good saver through the summer as it drops down the blue columns. The cooling energy that you're using through that season, it actually doesn't help a whole lot in the wintertime. I thought that was kind of interesting. Also, if you notice the blue, if you draw a line over the blue, you get a pretty healthy sized section of area for cooling. So this looks pretty cooling dominant. It's actually a lab too. So if you were to take that lake cooling effect system and put on this, most of that blue would drop down to nothing. And the pumping energy, of course, would have to go up, but it goes up a fractional amount. So I just want to bring up the district energy option. If you have one in your area, I think you should consider this. The first thing that I want to bring up, which is sort of I call it an issue in the industry, is you are not buying a utility, you're actually buying a product. So you're not buying kilowatts and making something with it, somebody's doing that for you and delivering to your door. And that cost includes all the above to make that happen. So the cost to build a chiller plant or a heating plant, I'm talking thermal in this for the most part. The cost of capital, the operating cost, all those things are wrapped into that. So I sometimes get people focusing on, here's what I pay in utility cost to make chilled water, but it doesn't always tell you the total picture. Another thing that is important is the cost of real estate for your building. This goes back a ways, but in the 90s, I used to work in Cleveland. They had a building they called the Chisel, one of these glass buildings with the upper part of it kind of came together, the tower's up on the top. And these hot water boilers were on the top floor with this glazing to see the whole skyline. And I bet that would have gone for premium cost per square foot if you could get rid of that. So anyway, things to consider. Also, when you are designing your building, consider what your level of redundancy needs to be. So if you're building tenant space, it's different from building a hospital or building supercritical CDC where everything has to stay inside the building where it's supposed to type of operation. So I took a couple of pictures off the net, and I don't know if this generator stack really exists, but that's a lot of generators. I think there's about 20 in there. I lost count as it got into the distance of the picture. At any rate, each one of these stacks up to cost money to your building, so you have to consider what your level of redundancy needs to be. And I want to point out, when you buy this stuff, you got to maintain this. I've been in a couple of situations where the switchgear had not been maintained, and the electrically operated switches, if they don't get enough attention, sometimes they won't switch when you want them to, and that's a big problem. That will let you down every time. So another critical issue is to make sure you have maintenance space. Hopefully everybody pays attention to this. I know it's real estate, but it comes back around over the life of the building. If you can't get a tube pull, you can't get your leaks fixed, that high performance building's not going to be high performance for very long. Same thing for, I had somebody back up a burner head to a steel column, and they couldn't get the door open all the way, so you couldn't get to the igniter part of the burner. Another thing that's pretty important, I think, in our industry, that isolating valves, you want to get an isolating valve that isolates over the life of the equipment. And this is my opinion, but the rubber-seated butterflies of the industry today, I'd consider them good about 10 years, and then they're going to start causing problems. So if you need that to run and isolate for 20 years, you might consider something better. Also, this largest component out maintenance strategy, it's a process where if you get your chiller stuck into a room somewhere in the basement, that compressor needs to eventually come off and get rebuilt. So you need to make a plan, make sure there's a plan to get that out, and so it's serviceable. Connectivity, this has probably been prevalent for 8 to 10 years now. When you're buying equipment these days, it comes with an LED panel, it comes with circuit boards, electronics, and all that is good, important stuff. It makes it more valuable if your maintenance staff can see that from their office. So there are some challenges to making particular equipment work with particular control systems. So your BAS, just something to think about, has to, in order for that to be visual on your front door screen, has to be able to connect with your control system. I'm just a plug for trying to make this work remotely. Our maintenance staffs are always getting thinner. I don't see that trend changing. Having somebody available when he gets a trouble call on the weekend to be able to look up before he gets in the car and goes has value to it. So once a building is ready, start the testing. This is kind of formalized as a commissioning has value. Commissioned buildings typically work, or at least you know what doesn't work. It needs to be fixed. There's a process that goes through, and one of the challenges of that process is to get contractors to fill in the blanks so we know that things are checked out. Your vendors have come in and started up your equipment, put all the settings in, and you're ready to run it through the strokes. And I'm putting a plug in for training. I'm getting to the point where I'm willing to get somebody from our office to show up during a training and stick their video machine and get it recorded, put it on CD, and give it to an owner. Because within a year, I'm getting questions about it because there's new people that have come on board. So almost, I won't say it's a free service, but it's value added just to try to provide some continuity. Going on with this, making a commitment to train your personnel. We did we put on a seminar in Houston with the UT utilities manager, Juan Ontiveros, and I believe his statement was he's invested $500,000 into operator training. And granted, that's a much bigger system that includes power, heat, and cooling, but that's the kind of investment that needs to happen for a system that's that big. Scaling that down to a building, you can call on your local vendors. They have training programs available that you can send your people to. And I would also promote for promoting within to help, again, provide that continuity. I think I can go to a retirement party about once a week, and I'm not 60 yet. So that's a trend that's happening in our industry. What does that mean? We got a lot of fresh faces that we need to, and we have a lot of new equipment. It's the days of the high fire boilers are quickly disappearing, and the days of the circuit board are upon us already, really. So that last comment was the district energy option actually simplifies this to a great extent, because now all you have to do is operate pumps, a heat exchanger, a fan for an air handler, and a control system, of course, to keep that high performance building running. And so just some conclusions. A commissioning building is a building that works. I don't want to, this is again my opinion, but our public bidding process feels like it's a little bit on the walking with crutches side, because when the job is done, trying to get that building to operate the way it's intended is a struggle. If you are a private entity, I would encourage, I had a vendor mention this, I would encourage inviting construction teams in as negotiation. There's several different paths to do that, and that negotiating process tends to make buildings work as intended when they're done. Oh yeah, and I had another. If you're interested in the lake cooling effect, that came from this 2015 presentation from International District Energy Association on lake source cooling at Cornell University. And with that, I think we're ready to go to Mitchell Swann.
Okay, I'm going to stick this here. There we go. So, I'm going to talk about, Tim talked about from design perspectives. I'm going to talk a little bit about from sort of the big picture of risk. My name is Mitchell Swann. You may have guessed that by the slide. I take a little poll of the audience. How many people work for design consultant firms? Okay. How many people work for contractors? Okay, let's see, they're worth a lot more. It takes 12 design guys to be one contractor. How many people work for any owners? Anybody work for an owner who will admit it? Okay, great. Institutional type owners, big owners, all right. Equipment manufacturers and vendors, all right. National Football Conference or American Football Conference, that'll determine what you watched yesterday. The AFC, I'm from Philadelphia, so we're going to be busy this afternoon. Dallas lost. Yay. So I feel much better right now just on account of Dallas losing. So just try to get a sense of where everybody's coming from in this. So I'm going to talk a little bit about the risk aspects of picking these things. I'm going to go through these objectives because we've kind of talked about them. Boom, going to go to this risk overview. Basically, you need to kind of actively think about risk profiles on the project. And there's two different, well, not just two, but multiple ways that you can think about that. There's obviously a design element, the bits and pieces and, redundancies and different types of equipment. There's also a bigger picture, how your plant fits into the overall operation of, let's say, a campus, or, as we talked about, lake cooling. There's a big one up in Toronto. They did an interesting thing up there. Tony Rocks at them. It was a great design. These cools downtown Toronto. They pull the water from Lake Superior. When they put it in, the water goes from the lake to the reservoirs that they use to make drinking water. So, and it goes to heat exchangers to help make a cooling loop for Toronto. This is sort of looking around corners. After they did this, One of the great things they wanted to do also was to get people to conserve, including conserving water. So people stopped watering lawns as much or washing cars as much. There's an issue, though, because if people stop drinking water, the reservoir doesn't get filled as often, which reduces the flow coming from the lake through the heat exchangers. And what they forgot to do is put a valve and a pipe to bypass water back to the lake. And what they started having a problem with is not having enough flow going to the reservoirs to satisfy the cooling load in the downtown. And so they had to add chillers to the thing to buck boost the line to give it some capacity. And that's one of those sort of, oh, we hadn't thought about this idea of what happens if we conserve water. Because I asked them about that. I said, well, why don't you just put a pipe? You already had pipes coming out of the lake, big valves, all that. Just put one going back. After the fact, it seemed like a good idea. But I mean, it was one of those things of like not thinking about the ramifications of the impacts of things. So when you're looking at your risk profiles, you want to look at your project risk, but also large operating risks. Qualitative, things that make you feel good. Quantitative, things you can count, okay? And then you want to kind of continuously monitor that stuff. This is a simple or a sample risk matrix, and I'm sure people have seen this before. High risk, high frequency, moderate risk, high frequency, that sort of thing. Low risk, high frequency. A thing that we often don't really think about are, we overdo some elements of rare occurrences and high impacts. Okay, we worry about getting hit by meteors. And we sort of downplay some of the items that are sort of more moderate impact but frequent occurrences. I wonder how many people, when putting together a central plant and the gear and electrical service, look into power outages from the utility. Okay, because I mean sometimes people don't think about that. And that was an item I think you brought up, Tim, dual-ended switchgear. And depending upon how you're planning on using your plant, your consideration of that risk may change. How you look at it differs, okay? But a lot of times people don't look into power quality or power dips from the utility as a function of their central plant design. This is when you start filling the thing out, it can get more complicated, okay? So that's just a sample of that. And then I want to talk a little bit about some risk considerations. Redundancy often has an internal driver and the concept of reliability. How much uptime or downtime can you tolerate? Uptime do you need, okay? You talked about a containment facility, and for let's say a BL3, you know, that's got to be continuous. You can't really take any downtime on that. So you have to think about the reliability aspects, and that's redundancy. And then you also have to think about flexibility, variations in load, like people don't use a lot of water, and the next thing you know, you don't have enough cooling for downtown. That is not necessarily a redundancy factor, but one would consider it sort of a reliability because that chiller system or chilling system is dependent upon an outside, unrelated activity that drives it. So that's sort of a thinking through. So you want to think about load variations on your equipment, and those can work together, okay? So you have to think about that sort of consideration. Load variation, how you size your equipment and your systems configuration, how much work around, how much am I willing to spend extra to work a system around so I can operate going the other way. Done that a lot with data centers, oversized pipe loops under the floor and connect the ends so I can run water into the data center from two directions, okay? It costs a little bit more in pipe, but the comparative value of the data center's operation, what it is worth to the organization, quickly strips out the pipe cost, okay? The other concept that's becoming a much hotter topic is resiliency, okay? And I know in Philadelphia and other municipalities, there's considerations of public buildings or quasi-public buildings like schools being places of safe refuge for citizens. So natural events, natural disasters, and in sort of climate adaptation. I know some coastal cities are looking at resiliency more. And how many of you are familiar with Hurricane Sandy when it hit the Northeast a couple years back? I guess that was, what, 12 or something like that? One of the big things that happened in New York, lower Manhattan, which is fairly low relative to sea level, matter of fact, Battery Park is all recovered ground. One of the things that happened is a lot of generator sets in a lot of buildings were in the lower levels. Well, the water filled the subway tubes. There's not much in the way you can run in a generator underwater. So they lost a whole lot of backup power. They built all this backup power, and it got scuttled by the fact all this equipment was below grade. Now in New York, you have to put those systems above grade, and you're back to discussions about value of real estate, because New York is a very expensive real estate market, but somebody figured out that it's even more expensive to have hospitals shut down, so we're not going to do that. So they moved all that, they're moving that stuff up, but that's a resiliency, an adaptation. They're making an adaptation in system design to weather, okay? And then, of course, there's man-made events. ASHRAE has a standard, I think, on protecting HVAC systems from biological and chemical attacks, okay, which is a completely different beast than what we're used to thinking of in most of our buildings. So I think when you're working through the risk profile, you need to look at things that are essential, sort of life safety that comes from code, okay? Then there's things that are essential to your operation, which may not be addressed by code. So don't think of the code as covering your operation. It does not care, really, in the most part. Important functions, things that are really important for you to do, and handy functions, things you'd really like to be able to do, but you know you could let it go if it comes to that. And I've put in systems with gear that helps to make that selection by monitoring loads, and it'll start re-adding buses on emergency power based on what capacity is available and where the loads were before. So you can get equipment and systems to help you do that. There's a duplicate slide, which I didn't get them to take out, but that's okay. Then I think there's a very important aspect on the operational intent. What you think about in terms of emergency operation or how your central plant's going to be configured is going to be impacted greatly by how you intend on using the thing. Is that mouse on the screen? There it is. Let me get you out the way. Okay. I'm sorry. I didn't realize I was sitting there blocking you all. Anybody here running their central plant in sort of a microgrid or an island operation? Is that the intent? Okay. Because some people on a campus situation, you may want to do that. When you do that, an always-on system in a microgrid, your central plant is a microgrid for you, you may view the utility as your backup, as opposed to thinking of your gensets as your backup and the utility as your primary. So that may lessen the need to kind of bring dual services in, because you're looking at the utility as a standby. And I mean, Philadelphia's Navy Yard has a microgrid. So they have the utility coming in, but the utility is fundamentally a standby. All right? You may be doing some demand management. How many people doing that? Anybody doing demand management and kind of selling power back to the grid or selling capacity back to the grid? We did peak shaving and peak shifting long ago, and now we're starting to do more things on the demand side management. So you want to think about matching your system configurations to your loads, peaks, and things like that, so you can turn equipment off in a rational function, a rational relationship relative to what your load profiles look like. It's the importance of that modeling that you pointed out. And then from an emergency operations perspective, am I going to island and I'm going to operate no matter what? Okay. Talking to some guys about a microgrid at a university in central Pennsylvania that's designed to carry the student physical education center, because it's got showers and all that sort of stuff, food service, and 2 dormitories, because a couple years ago, they had a big ice storm in Pennsylvania. Students couldn't get home, and they didn't have that capability, and they were using propane on a lot of their buildings. They couldn't get propane in, and suddenly they have people there for 4 or 5 days. It's getting chilly, and they're getting hungry, and they're getting grumpier every day. And they said, boy, you know, we're charging parents a lot of money to come to our private school, and here it is, we can't keep it warm, and the kids can't get a shower. So they redid some central plant operations in order to carry that core element, so they have a place for sort of shelter in place or safe refuge for the, well, shelter in place, I guess you'd call it for that, for those students, so that in the event of one of those ice storms, they could condense the campus to some place where everybody could stay warm, dry, fed, and have a place to sleep. So that's changed their consideration of how their plant was configured and how the operations should go. So those are the kinds of things that, from a big risk perspective, big risk profile perspective, you want to think about. Your operational content and how you plan on running your plant. This is how this stuff looks when it starts getting complicated and you start factoring things in. Some of the risk elements can be, I guess I'll say, hard qualitatively developed. Outages from a utility, things like that. You can talk about mean time to failure for equipment. Some things are more qualitative. How often do we have certain sort of squishy problems that you have to sort of make a judgment call on your own? Is that 60% likely, 70% likely? You know, things like that. You'll have some that are hard, some that are a little bit softer numbers. And like I say, you can put them together in a couple of different ways. If you actually look at some of these, the side portions in the gray, they'll talk about governance risk, construction risk, demand side, so things inside the operation and outside. Then there's force majeure, okay, which is acts of God. How much do you want to consider yourself absorbing those? That's sort of the resiliency question, I guess. I could look at it that way. Resiliency is more of a force majeure considerations. So there's external versus internal. Some you can control and some you cannot. Weather, for example, you cannot. Quantitative and qualitative. Reliability is not necessarily the same as redundancy, all right? Although one can think about having redundancy to make a system more reliable, but buying certain types of equipment makes it more reliable, not necessarily redundant, all right? And flexibility is not necessarily resiliency, although it can aid and abet that process. So if I put in a boiler plant that there's a difference between N+1 and taking my load and dividing it up into 3 at 40%. I don't have N+1 boilers, but I do have the ability to limp along should I lose one. So I'm flexible and somewhat more resilient. I can take a hit and not have everything collapse. There's a major university in Philadelphia that has a couple of central plants. They're tied together in a big loop, and it's designed on the idea that if we lose one, we're able to shift capacities around so that we might, have to cancel a performance at the theater or something and turn that building down, but we're able to limp along by rerouting things through the circuit. Does it cost a little bit more money to put in? Yeah, it does. But you really need to measure some of your, those kinds of costs against the costs of downtime. And that is actually somewhat a very difficult process. I think that Tim mentioned a little bit some delivery methods, sort of. One was, so you talked about DBOM, design, build, operate, maintain. Anybody looking at central plants provided by an outside vendor, so to speak, to your operation, where you get into what we call a DBOM, design, build, operate, maintain contract? A central vendor or some organization will build and operate your central plant, so that outsources all your maintenance and all that on the plant. What that does from an accounting perspective is it takes the capital cost of that construction, moves it off book, and puts it into an operating expense, which can make your project budget look better. So, I mean, there's different ways to kind of, skin the cat, so to speak. But there's some things you should, look at in terms of how you want to have that central plant operate. At the end, I say, learn to see around corners. I think a thing that we sort of miss in this industry is we do a pretty good job on lessons learned. We kind of, at the end of the project, we sit down and talk about everything that went wrong. We're not so good on the front end side. And we've started talking to people about, I guess you could call it, instead of a post-mortem, which is what the lessons learned is, a pre-mortem. Before you do the project, think of everything that could go wrong. And then you can start ranking that stuff. Some stuff, a meteorite could hit us. Well, okay, there's not much I can do about that. The odds are pretty slim. But I can make a discussion about, well, we could have a labor problem or a delivery problem, or it could be whatever, getting equipment in. Okay, how do we resolve that? How do we deal with a chiller that we have to rebuild the compressor, because we know we're going to have to do that? A thing that, you know, I've had discussions on projects, closed machines, hermetic machines versus open drive machines, okay? Open drive machines cost a little bit more, but if I have to rebuild a compressor, I can do it a lot faster because I don't have to evacuate the system and purge the refrigerant loop. How important is that? How important is that time window to you? Okay, how important is recovering from that hit? So those kinds of questions pop up, and they're worth discussing from the risk profile perspective. And it might take, you know, 2-3 days for everybody to get together and kind of mull over it, and you'll start dropping stuff to the bottom of the list. Things you can worry about or do something about, things you can't, and things how much you're willing to spend. At what point are you going to go, okay, I give up and we're going to let that go? So that's the big picture aspect of risk. It's critical on all aspects of the project, but incredibly important when one looks at things from a central plant that's, you know, core to maintaining your operations on a campus or core to maintaining your operations in a critical facility. You really do need to think your way through that and challenge your own assumptions, which I think Tim brought up. So I think we're going to keep going, try and keep our schedule. We're going to push to accelerate, right? We're going to put extra people on the job and stack trainers. Terrence Rollins was taking a circuitous route to the podium. He's getting in his Fitbit steps. I'm going to go up and down this thing here, and I'll pick up a couple flights of stairs. Look at that. Boy, he's made the loop. Vasco da Gama here. Come on up. Here we go. All right. Here you go. I'm going to try and get this. Okay.
Good morning, everyone. How's everybody doing today? Can everybody hear me? Sounds all right. Sorry your teams are out of the playoffs, but it's an opportunity to piggyback and root for the Philadelphia Eagles, right? The underdog, the year of the underdog. All right. Okay. Thank you. Some great action from our experts. We're going to accelerate a little bit and get to the professional development questions, the first that are online. So I'm going to hit this awesome switch. You're very familiar with our workshop that you've seen information online. We're going to get right to the proceedings and to the case study. We know what the objectives are. We understand. We know who our expert panel of experts are. We want to thank Mrs. Sonia Pouncey, our track chair, for allowing us to serve under her leadership to put this outstanding presentation on to your design experts. Thank you. Okay. You're familiar with the outline, the construction operations and maintenance of central plants, large central plants, distribution systems. You want to understand the value and the maintenance instructions for those large systems. You want to examine those. You need the doctors, the forensics experts here, and the risk experts here. You also want to, when you're dealing with large central plants, the ties in Technical Committee 6.2, 7.3, and 9.1, the trifecta. We're looking at big picture stuff here, okay? We want to be able to also coordinate with our expert electrical engineers from the IEEE to understand our high voltage systems, medium voltage systems, and what it's doing downfield. Daily testing, monthly testing, weekly testing. So this morning I'd like to reference the ASHRAE handbook from which to write, cite, train, paraphrase, research, instruct, and present. The ASHRAE 2015 Applications Manual, Chapter 39, Operations and Maintenance Management, which falls under Technical Committee 7.3. So we got a case study today. Prior to performing your operations and maintenance open heart surgery, you're going to consult with your master construction builder, Mr. Anderson. You're going to also coordinate with your master forensic reverse engineering expert who just spoke well of risk, Mr. Swann, and don our gloves and our boots and go into these central plants and try to find out what is the history of this plant now this O&M staff has changed over. Refrigerants have changed, owners have changed, people have come and gone, and now we have new refrigerant mandates. We used to have what? R11 in our big centrifugal plants, right? In our laboratory at Cass Technical High School, We used to put R11 in the beaker and put orange in it and watch it freeze. Can you do that with R123? No. So now our research and scientists says the replacement to help us reduce our greenhouse gas emissions and our global warming potential is R514. In this particular isolated case study, this particular plant has reached the useful end of its life. Therefore, we're going to bring in our experts, say, what is the risk if we go and write a sole source selection for an existing plant to bring up the new technology to meet the new energy model, because the cost of energy is increasing, and also the resiliency of this top secret facility that we're able to maintain containment in the BL4s if there is a natural occurrence. Does that make sense? Right. So we have these softwares and tools now that are non-proprietary, Excel, our old long head calculations, our computer models, and we're going to go back to one of our original equipment manufacturers representatives who has the case study in order to develop that particular plant and say what was there from yesteryear 20 years ago. Can we design a system to meet the same footprint and the mechanical pads with a little bit of modification piping, a little bit of electricity, and also to upgrade our electrical power systems to give us a new high-tech performing systems. A couple months ago, some of my buddies was at Tyndall Air Force Base in Florida, had to evacuate. They ran into these situations. These are real situations that are happening today. And then when we introduce the district energy perspective to it, we don't want to repeat what happened in New York. We don't want to repeat what happened. So we're going to go back into the file, as Hannibal, the HVAC Hannibal says, he's back on the case. We're going to pull out the tools, and we're going to look at our profile, because now the KW per ton of chillers 20, 30 years ago, they're outstanding now. They can make them to whatever you'd like to meet the production possibilities frontier. And this is an example of one of our manufacturers' non-proprietary information to analyze our chillers. We can send this to you under separate cover. And more importantly, our electrical switchgear. This is a typical switchgear from the main power company coming from PECO. Now we want to put 2 of these in place, double in the substations. We want to be able to introduce microgrid, switch from Pepco, also bringing a live feeder into Baltimore Gas and Electric. So if there's one line goes down, this facility, outstanding, will always be able to have power. And when there's a load curtailment, we say, well, we have this third-party agreement with our energy professionals from Ideal in this microgrid perspective. We're going to make our own power. We're going to be self-reliant. We're going to sell power back to grid for our poor hospital downstream where it has the babies and everything. And we're going to be self-reliant. We're going to have third-party contracts to talk to PJM, electrical engineering experts. We love our IEEE experts. They are our brothers. We cannot do without them, right? Okay? So we have to be able to look at the big picture. Okay, those BL3s are very, very crucial. So are the chiller operations. Have you had a building that ever went down emergency power? The humidity and the temperature went so high in the building you had to evacuate it and took how many hours to bring it back down? Right? Okay? This is a grid of a particular plant where everything can be is in that particular facility. This is just a view of what's there redacted, of what a typical plant look like, where the generators are, emergency sequence. So what we did when we implemented the emergency management program is Mr. Anderson is quick to convey that we had our teams at every switchgear, every station coordinate with local authorities, having jurisdiction, that we're going to do a live simulation test as if people are in those buildings before we turn it over to the customer. We're going to man and female man that particular building with our experts and record the documentation. That's why it's important now that ASHRAE has an operations, maintenance, management, performance, managed maintenance program certification to reduce the capability gap between the infamous experts in Chapter 39 and the behaviors there and the Association for Facility Engineers. We want to increase enrollment and participation and find that junior engineer that's working on his or her EAT before they become a PE to spend time with operations and maintenance staff and understand the behaviors of the facility and videotape and film the commissioning and operations of that building before you turn it over. Does that make sense? Has anyone ever experienced that? Who's had that opportunity, that problem? You leave, you disappear, next thing you're getting calls, now you gotta go spend more money to fix what you designed. Now you got that beautiful chief engineer who has been operating for 30 years, who went to school at night, and became a mechanical engineer, wants to tell you how to design and operate your buildings. So you're going to take that young engineer and that mid-career engineer, and you're going to have them learn this certification to do what? To be able to understand what happens when you have these priority loads. What happens? This is typical. The question and answer session will take place when we're done. But what we'll do is we're going to look at these particular situations, what happens as soon as that power went out. We want our priority critical systems to be operational immediately, no question. You don't want to lose contain. What happens when you lose contain? We don't want to say we have occurrences, and then we also have life insurance policies. So these are some of the situations that Mr. Anderson spoke of in his presentation. This is strictly from the IEEE 44466 and Emergency Power, the Orange Book. The Orange Book is our Bible for emergency management electricity, the Orange Book. Okay, priority 3 loads, priority 3 loads. When do they switch in? When do they kick in? Okay, depending on what you have, it's relative, whatever you have. We also want to look in the end of load shedding, when it's accomplished. Peak shaving of loads of a chiller plant, right? If you have a building with no windows, how are you going to open windows at least get some of the fresh air? You can't do that anymore, right? So you're going to call those people. They're going to be on emergency match. They're going to respond. They're going to have Palm Pilots. Going to have everything, mobile trucks. They're going to practice this test every quarter, depending on what your building owner wants you to do. So that means that you stay engaged in your designs. And then you go back and repeat performances 10, 20 years later from buildings that you designed. That's where we're going. Okay? This is a particular case study look at. We have a typical R123 with the kW per ton, constant volume. This is what we're going to upgrade to our new action now. Okay? We're not going to get details because we're pressed for time. I'm going to get to the Q&A session here pretty soon. Okay? Typical sequence. Everyone's familiar with chiller plant optimization, right? We all now know that chillers can operate much more efficiency if we lower the condensing water temperatures, according to Mr. Swann in his 2002 testimony about the risk. You need to investigate those risks associated with that behavior of your plant and the mission that you're designing your facilities to. Don't you want to stay engaged downstream of your buildings and don't let the O&M contractor or some other new engineer come and redo your engineering design? You want more referrals. So train your junior engineers to be operations and maintenance professionals under the ASHRAE certification standard. This will cut down the capability gap, okay? This is what happens on a further decrease in temperature. What happens? We bring that other chiller on. An emergency scenario, we want to shed loads, but we need to have our current loads 100% capacity. We want these chillers operating all the time, okay? We may not be able to do that in some cases. This is a particular, someone wanted to see some math of previous presentation, so here's a train trace analysis which can send to you of a particular plant and its deal points. Here's some of the throughput of those particular deal points of what we're saving, that greenhouse gas emissions. And here's an Excel cut and paste action of a big file that is very deep to give us the deal points to help us make these decisions, okay? We also are going to pay Mr. Anderson and Mr. Swann to continue your stake because they're our lawyers. They're going to protect your design. This we will defend. We got the best defensive coordinator engineering experts in the world at this table. We need to leverage that experience. Okay, I'm running out of time here. They're about to throw me off the stage, so I'm going to get your Q&A real quick in your briefing papers for those that are listening. Okay, question number 1, emergency power sensors are designed in accordance with whom? IEEE. Great answer. IEEE, right? 4666. All right, when replacing R123 centrifugal chillers with replacement refrigerant, which one we're going to use? We're going to consider. Good question. R514A. Okay, emergency power system designed for a system readiness range of what? 1 to 2 hours or 24 hours, depending on what we're doing, right? New technology, okay? Emergency power, high voltage, and medium voltage priority 1 loads are from what? 1 to 30 seconds, okay? Load shedding is accomplished by what? Peak shaving loads. Number 6, kW per ton, a high efficiency chiller is what? 0.68 kW per ton, 63 kW ton, 0.58, or 0.532 kW per ton. Okay, which ASHRAE guideline is used in the commissioning process? Anyone? Someone said 1.1, someone said 0213, 1.1. Okay. Question 8, which ASHRAE guideline is used for HVAC technical requirements of the commissioning process? Anybody? Who said that? Question, what's that again? 013, okay. Number 9, which ASHRAE guidelines cover the preparation of O&M documentation? Guideline 4, 08. And lastly, which standard covers energy, our favorite, energy efficient in existing buildings? ANSI, ASHRAE, and IES standard 100-218. This concludes our block of instruction for this information. At this time, are there any questions? I know they're going to kick us off the stage, so we have to play a little bit better and make a little bit more noise. They keep downstream. Any questions at this time? Sir, I believe there was a question over here, sir. You had a question? You sure? Okay. Anyone else? Sir, yes, sir.
Larry Spielvogel, engineer from Philadelphia. Mitch mentioned the very attractive term of microgrids, and he mentioned the Navy Yard in Philadelphia, and it turns out I have some clients there. And are they ever getting screwed? Because the microgrid charges twice as much for electricity as the local utility, and once you're locked into a 20 or 30-year lease, you have no choice but to pay. And so we need to talk about the downsides in addition to the upsides.
Any other questions?
CL Chonghui Liu, Property Design Group, Syracuse, New York. So regarding that priority load you're talking about, I'm not very familiar with that from IEEE. So is that kind of pretty much industry standard? My experience is pretty much just from the owner's preference. Like Mitchell was talking about the dorms, whatever, the gymnasiums. So just wanted to see what's your experience on that.
Thank you. That's a great question, sir. That from IEEE is a standard based on what you're designing your facility, the type of facility that you have. Some facilities, such as national parks, do not have emergency generators. If there's occurrence, it just happens, it goes down. But in your particular confidential situation, it is important to find the latest and greatest, working with IEEE, to be able to design your building to meet those objectives, okay? So you may have a top secret mission critical facility data. How is it important to keep that data? That data is important to that structure, that business, right? So they always want to keep money and cash flow going through that exchange. So your systems may have immediate redundancy. I think I'm going to pass the mic here because our experts is here. Yes, it's important to have those systems ready. Of course, the more resiliency they want, the more it costs in the design. So we created a new production possibility frontier several years ago. We created something called the 3A's affiliation, ASHRAE, AEE, and Associated Facility Engineers. So I changed the formula now to say ASHRAE, Association Energy Engineers, the Institute of Electrical Electronics Engineers, and now IDEAL, through their opportunity for approval, has given Mitch Swann exclusivity and Mr. Anderson and Ms. Pouncey the ability to tap into that resource, to put that back into the organization to meet those situations, to reduce the occurrences for the catastrophic failure. Does that make sense? And that's a worldwide phenomenon, correct? Any more questions? Go Eagles!